Hello, welcome to another episode of Building SaaS on AWS. I'm your host. My name is Derek, a developer advocate at AWS. And if you've seen the show before, you'll know that this is the show where you come and find out tips, techniques, and patterns that you can use when building your SaaS applications on AWS. If you've missed previous shows, you can still check them. Check them out here. I'll show a little link to past shows. You can check out my YouTube channel and grab the past episodes. Some fantastic content in here. Now, today, we're going to talk about shuffle sharding and SaaS, and I'm joined by Anton. Anton, would you like to introduce yourself?
Yeah, absolutely. Hey, thanks, Derek, for having me. Hey, everyone. My name's Anton, talking to you from sunny Austin, Texas. Right, I'm a principal solution architect for serverless stuff here at AWS. Right, I'm primarily responsible for the central part of US and also ISVs. Right, so in my daily job, I work a lot with ISVs, and as you can probably guess, ISVs in many cases equal SaaS.
Sure. Thanks, Anton. Well, really nice to have you on the show. Very exciting, a very exciting topic as well. So we're going to start off with a bit of a level set. If you've been in the software game for a while, like I have, I've got lots of white hairs. I've used shuffle sharding before, but not everybody has. So Anton, I think it's probably a good place to start is some level setting on what is shuffle sharding. You reckon you've got time to just bring it back to first principles and explain it to the audience?
Absolutely, absolutely. Now, before I do that, right, because we want to make this, a little bit more interesting, right? Do you mind sharing my screen for a second?
Yep, sure.
Okay,
I like
so
this.
I want to be showing, I hope it's not too small, right? But I'm going to be showing a series of demos today, right? Because I do want, some real stuff to back me up, right?
Of
When I'm
demos.
talking about the theoretical stuff, right? So what I'm going to do in the background is I'm going to start JMeter, right?
Oh,
And I hope most of you are familiar with JMeter. It's a tool for load testing, right? And the only thing that you need to know at this moment, right, is that I'm simulating 20 tenants, right? We're talking about SaaS. We're talking about multi-tenancy. So I got tenants 1 to 9 as one group, and tenant 20, which will be a little bit different. And we're going to be talking about how different, why tenant 20 is different, throughout the day. Okay. So
okay.
I think that's, all the screen sharing we need to do for now. I
Nice.
just want to make sure
Nice.
that everyone is aware this is running in the background, as we start to discuss. Okay.
Yeah, cool. If, like myself, this is like a step back in time. J Meter, I have not seen J Meter for a very long time, and I see by the UI that it hasn't changed much, which is really a nice, comfortable feeling when you see something.
I'm taking this as a good thing, right? So yes, JMeter is a tool that I've been using it for probably as long as I can remember. Okay, there are other tools, right? A little maybe a little bit more popular today, a little bit more modern, like Artillery or Locust for
Yep.
Python stuff, right? But what I particularly like about JMeter is the fact that the way it visualizes stuff, right? I couldn't find, maybe there is, right, but I couldn't find an alternative that gives me stuff in such a visual way when I need to visualize it.
Yeah,
Okay.
nice. I wonder if anybody watching has actually used JMeter. Give us a wave if you've used JMeter before. Just to reiterate, this is a live show, so we love to hear some your questions as we go. So anyway, enough about JMeter, Anton.
Yeah.
Well, I'm sure we'll see it a lot later as we as that load goes through the tenants.
hmm
But let's get
hmm
back to shuffle sharding and the reason we're here.
So let's talk about sharding, right? Let's start with talking about sharding in general, right? And then we'll talk about shuffle sharding, right? So, without diverging this discussion too much, right? How did I get here, right? Well, as I said, right, I work a lot with, major customers, ISVs, right? Customers who are building SaaS on cloud, right? One of the very important topics for them is properly doing multi-tenancy, right? With fault isolation, right? With additional resilience, right? Because as when you start your new piece of software, right, those are the things that you're obviously looking at, right? But they're not necessarily top priority for you, right? But as you grow, right, as your product becomes more critical for your customers, right, those nines of availability and reliability, you obviously
Yep.
want to have more and more and more and more of that, right? So shuffle sharding, right, and sharding in general, what was one of the things that I've investigated, right, when I was trying to find additional ways to find the customers I'm working with. Now, the idea of sharding is it's not new, right? Unfortunately,
Yep.
I cannot claim that I've invented sharding. No, not at all, right? It's a pretty it's been in the industry for quite some time. And the idea is you take something whole, right? And it's originated actually from the databases, right? You take something whole and you break it to pieces, right? To shards, right? And the idea is each of those shards can be used on its own, right? So imagine, for example, and a simple scenario where you have a database, right?
Mhm.
Let's talk relational database with ID column, right? And four different data columns, right? Well, what you can do is to break that single table into two different shards, right? So you will have ID column in both, right? But one of them will have a subset of data, and the other one will have the remaining subset of data. What it actually gives you, right, is additional resiliency, right? If one of those databases, one of those shards is down, right, your system is not fully down, right? Your system can still partially operate, right? And as you take this idea forward, right, you introduce more shards, right?
Yep.
The number of shards grow, right? You introduce additional resiliency per shard. This actually becomes quite a powerful tool, right, to improve your resiliency, to improve your fault tolerance, in a cloud world. So I hope
Cool.
this answer your question. Yep.
Yeah, for sure, for sure. Great explanation of sharding. The next obvious question, Anton, is how does it apply to SaaS? What we're talking about today, and more specifically, tenant isolation.
Absolutely. So anyone who've ever built SaaS, right, is going to be familiar with the models, SaaS models that I'm going to be talking now, right? So SaaS, in many cases, equals multi-tenancy, right? When you're providing software as a service, you want to provide it for multiple tenants, multiple customers, multiple users, right? So there are different levels of tenancy, right, in many cases. Now, there's a classical model, right? Or, I'll call it classical, right? And the idea is you take a product, right? You put it on cloud, right? And for each one of your tenants, you provision an instance of that environment. Right.
Yep.
So let's say your product is a, Java server or whatever, right? For each of your customers, you provision a dedicated instance of that environment, right? This will give you highest isolation level. Okay, obviously, right? But it's pretty expensive to maintain. Okay,
Yep.
because if you have 10,000 or 50,000 tenants, now you need to replicate that, right? It's super expensive to maintain. So
For sure.
it's common to look at the other part of the spectrum, right? So instead of taking single tenant solutions and just deploying them as SaaS in a single tenant way, how about we build something multi-tenant, right? A single setup, right? Single environment that can serve multiple tenants, right? The idea sounds pretty awesome, right? Now,
Yep.
obviously, it's much cheaper to maintain, right? Now you don't need to have an environment per user, right? But, as with great power comes great responsibility, right? So you're starting to see other concerns, right? Other concerns that you need to address, right? So, for example, things like data isolation, right? How do you
Yep.
deal with data isolation? A little bit different security model, right? And one of
Yep.
those concerns is the fact that if with environment per tenant model, one of those environments crashes or dies, or something happens, it fails, it affects a single customer, right? It does
Yep.
not a single tenant. It does not affect everyone. With shared model where you share everything, right? If part of your environment is down, right, it will affect every single tenant, right? Because all
Absolutely.
of them are reusing that environment, right?
Yep.
So the idea of shuffle sharding is to meet those two models in the middle.
Hmm.
Okay,
Hmm.
so to have a little bit of best of two worlds, right? To meet in the middle, right? You're not provisioning an environment per tenant, but you're also not doesn't do not have a single environment for every tenant, right? So you have a smaller number of environments. It's still multiple environments, right? Which is significantly lower than your number of tenants, right? So to give you an example, well, let's say, for 10, 20,000 tenants, you can have 10 on 20 environments like that, right? That's essentially the idea.
Nice, nice, and obviously, with that model, there's obviously there's trade-offs, and you talked about having to share tenants, and usually when we talk about sharing of resources, we talk about things like noisy neighbor as a problem that pops up. How does shuffle sharding, or what would you think about addressing when this question
So
inevitably comes up?
that's an excellent question, right? Because noisy neighbor problem was probably the main reason I started this investigation, kind of started to look into that, right? And this is not because, I Googled about noisy neighbor problem. No, this is actually came from a customer, right? From a customer trying
Yep.
to implement something to address noisy neighbor problem. They did want to have a multi-tenant solution, right? But, how do we address noisy neighbor problem? So, just, 10-second, explanation what noisy neighbor is, right? So if you've ever lived in like apartment building, right, you know pretty much exactly what noisy neighbor is, right? That's the neighbor who has a party like 11 p.m., right, or 2 a.m., whatever, right? Essentially, that's the neighbor that makes everyone else's life miserable. Okay, now taking this back to cloud world, right? Imagine you have 10 tenants, everyone lives in peace, right? Everyone loves each other, right? They're not bothering anyone, right? But suddenly one of the neighbors becomes a noisy neighbor, right? What it actually means, instead of sending, whatever 10 RPS that it was sending before, right? Now it's sending 20, 30, 40, 50,
Yep.
100 RPS. So what would happen in this case, right, is, resources are not unlimited, your cloud resources. Even in serverless world, right, which scales amazingly, right, and how how scalable serverless is, right? But even in
Yep.
serverless, right, resources are not unlimited. So in this
Sure.
case, what actually happens is that noisy neighbor takes a lot of resources for themselves, right, and
Mhm.
as a result, other tenants are getting less resources, so they will get lower RPS, they will get higher latency, etc. And actually, to illustrate that, let's create a noisy neighbor. We're about 10 minutes in, so can you
Yep.
share my screen again,
Sure.
if
Yep.
you don't
Let's do
mind?
that.
Okay, so what
There we
you can
go.
see here, right, is I got those 20 tenants running, right, and you can see that the number of samples is, roughly the same,
Is
roughly.
there any way we can
Okay.
zoom in a little bit,
Ooh,
Anton?
I don't know
Can
if
does JMeter have zoom?
I don't even know.
Uh,
I don't think it has Zoom, right?
okay. Yep.
But I do have maybe a slide I can show later that shows that. So let me
Okay.
explain what's going on, right? And yeah, I don't think JMeter supports zooming, right?
That's
So
fine.
so if you
Just
can
like a
see that,
Commodore 64 is only 4 F keys.
oh man, I think we're roughly the same age, Derek. I am getting your references. So if you can see here, right, tenants 1 to 19, right, this this group, this user group has 19 threads, which means pretty much every single tenant is getting a single thread, right, to keep it simple. Tenant 20 at this point also has one thread, right? But in order to make tenant 20 a noisy neighbor, let's change that to let's say 15 threads, right? So what's gonna happen, right, is tenant 20 is going to become my noisy neighbor for the sake of this demo. So I'm gonna stop the execution, right? Shut down 20 clients, right? And I'm going to restart it in a moment, right? It's shutting down all the threads, right? For those of you who are looking here on the side and seeing some charts, right? This is exactly what's happening, right? You can see that they went immediately down. Okay, it takes JMeter a moment to shut down all the clients. Come on, JMeter. Demo gods, right?
Hold on, we did. I didn't. We didn't toast the demo gods.
Yeah.
The demo gods offering.
Cheers.
Mhm.
Cheers. Okay.
There you go.
Okay. Okay. So, well, you can stop the screen sharing for now, right? I think, I've
Yep.
managed to explain the idea of what I'm going to do now. Okay.
Cool. Cool. Then
Okay.
what about people ask, is there actual a real world implementation for shuffle sharding? Is there anything out there that actually does this currently?
So this is actually an excellent question, right? There are quite a lot of implementations of shuffle sharding in the real world, right? And one of the examples that I love to give is Route 53, right? That's our own, Amazon service, right? AWS service. And I'm
Yep.
trying to fix the, the JMeter
You
problem here in the background.
you
Okay,
fix
so
that, and
yeah,
I'll Google
yeah,
Route
that's fine.
53. There we
Yeah,
go.
Route
Yep.
53, right? So to give you, to give you a perspective, right, what Route 53 does, right? It's a domain management service, right? This is where you manage your DNS. Okay,
Hmm.
but the way they've implemented it, right, they have a little over 2,000 virtual name servers, right? 2,000, right?
Yep.
And for each customer domain, right, they create a virtual shard, right, of 4 name servers. So think about it, right? Right. So for each customer, they are randomly generating a virtual shard, right, and taking 4 servers out of more than 2,000. Okay, as a result, right, a little math here, right? As
Mhm.
a result, they have a staggering number of combinations there, right? The number is over 700 billion possible combinations there, right?
Yeah, well,
So, even if one of those virtual servers fail, right, others are still working. Okay,
yep.
so this significantly adds to your resiliency, right? So Route 53 is a really good example of shuffle sharding being used at scale, right, in a real production scenario, right, that I would imagine most of the
Nice.
participants are familiar with.
Nice, nice. I think that's a good example as well. Very relevant. And I put a link to if you want to know more about that. It'll scroll along. If you don't get the link while we're talking here, you can check it out in the past episodes on my YouTube channel. So I think next, Anton, shall we dive into some architecture? Is that the next place to go? Do you want to jump in there?
Yeah,
Or yep.
absolutely, absolutely. Okay, so what I have, in store for you, for you today, right, for the audience is I want to talk about 3 models, right? 3 different architectures, right? One without shuffle sharding. Okay, so there is no shuffle shard, there is no sharding at all, right? The first model is going to be super simple, right? One environment serving multiple tenants. The second example, right, will show simple sharding, right? It's not going to be shuffle sharding just yet, right? But it will be sharding. Okay.
Yep.
And the third example, and that's the one I'm actually going to show live, right? That's the one I'm currently probing with JMeter, right? I got it up and running, right?
Nice.
That's the one
Yep.
I'm going to show you results for live, right? And, do expect a tiny gap in the chart there, right? Because it took me like about 2 minutes to restart JMeter, right? So, let's account for that as well, right? Demo
Yes.
test,
Yes. Jamie.
okay, let's hope they're going to be favorable to us. So I'm going to show, to save us some time, I'm going to be showing the first 2 environments, right, using slides, right?
Yep.
Because I think, it's not going to be, it's going to be all about architecture. Okay, so I hope,
There we
people
go.
will like those slides. Can you see my screen?
Mhm. I can. Yeah.
Okay,
At the minute, I'm
let's
seeing.
shift.
There we go. Single
Okay, okay.
processor.
Yeah, yeah, yeah. Okay,
You got it. Yep.
let's see here. Let's see here. Okay, so this is the first scenario that I've talked about, right? This is no sharding at all, right? And you have multiple tenants, right, using one processor. Okay, so tenant one, tenant two, and tenant n, whatever, right?
Mhm.
For the sake of these charts, let's assume the first tenant is the noisy neighbor, right? Or a tenant that is sending what we call poisonous requests, basically requests that are, you cannot process them, right? They will crash your backend, right?
Mhm.
And, if we talk about resilience and fault tolerance, right, you can probably imagine what's going to happen next, okay, when one of those tenants becomes a noisy
It's
neighbor. But let's
not
take a
going to
look
be
at
good.
yeah, yeah, yeah. I think everyone can understand what's going to happen next, right? But
Yep.
just to have a common ground, right? So not the solution, right, but a way to implement that. This is what the architecture that I've implemented, right, to prove some of my theories, right?
Mhm.
Super simple. I didn't want to overcomplicate it, right? I wanted to keep it pretty simple, right? API gateway that is getting requests from those tenants. Each request will have a tenant ID of sorts, right? API gateway will push those requests to the queue, right? We still love decoupled architectures. Decoupled architectures are awesome, right? And then you have a Lambda function that is pulling from that queue, right? The only thing that it does that falls under processing is thread sleep for 300 milliseconds, right? It emulates some sort of processing, right? And then it also, emits metric to CloudWatch, right? Because I do want to see the result of this whole thing, right, in CloudWatch. Now, what I'm going to be measuring here, and this is not just relevant for this first architecture, it's going to be relevant throughout the whole, all three of my experiments, is end-to-end processing time. The time it took from the moment request reached API gateway till the moment request was successfully processed. Okay. Make sense? Any questions so far?
Yep, makes complete sense. Yep.
Okay, cool. So let's take a look at what this is going to look like, right? So this is, CloudWatch dashboard that shows the behavior, right? And I've split it to several segments, right? The green area, that's what I call peace and quiet, right? Everything's okay, right? No noisy neighbors, no problems. And then we're getting into the reddish, right? Pink, purple, whatever area that I call noisy neighbor, right? And then you have a cooldown. That's where noisy neighbor decided it's not going to be noisy anymore. And then we're back to peace and quiet, right? The same approach will follow us throughout all three examples. Now you can see that, the moment I got noisy neighbor, right, all the tenants were affected. Every single tenant was affected, right? You can see that I have 20 of them. You can see that execution duration, end-to-end execution duration, starts to spike for all of them. And that's expected, right? They're using the same processor. So whenever that processor is overloaded, whenever that queue is overloaded and processor doesn't have enough capacity to process the data, right? Well, it's expected to see this spike. Right, essentially, processor doesn't have capacity to process the data, so we're getting more messages queued up in the queue, right? As a result, you can see that the execution duration grows for everyone, right? Once noisy neighbor stops, right, you can see that gradually execution duration starts to drop until it is back to normal. Okay. If you look at the actual numbers, this becomes even more interesting, right? Now, one thing I want to mention here, right, on the left in the green part, that's the decimal point, right? That's not comma, that's decimal. So this is millisecond, right? 387 millisecond, right? The number looks much bigger than the one in the red box, right? But it's actually much smaller. So you can see that, the execution duration, right, in the green area was less than 400 millisecond end to end. Okay. Now in the red area, right, and this is just one of the samples here, you can see that it's getting closer to 60 seconds, right? And, as I said, right, every single tenant is affected, right? And this is actually expected. If you look at the execution count, right, you're getting a very interesting picture here as well. You can clearly see that noisy neighbor, right? That guy that makes everyone's lives miserable. Okay. You can see that, yep, it's getting more executions processed because it's sending more requests, right? So, that noisy neighbor might be pretty happy, to get more executions processed. But you can see that it's actually negatively affecting every other tenant, right? And you know what? Even while it's getting more executions processed, it's still affected by this growing execution duration, right? So, even for noisy neighbor, that's not exactly the best case scenario. Okay.
Yep.
So how can we make it better, right? And we already talked about sharding, right? So what happens if I take my tenants, right, and I randomly distribute them across more than one processor, right? So I take, tenants 1 and 3 and I assign them to processor 1, tenants 2, 4, and 6, and I assign them to processor 2, etc. Other tenants, I'm going to assign them to processor 3, right? What happens if I have more than one processor, right? And my tenants are randomly distributed across those processors. So, I'm using 3 and 8 here on the slide for simplicity, but obviously the number of processors can go into hundreds and the number of tenants can go into thousands and, tens and hundreds of thousands, right?
Yep.
So,
Yep. I'll just stop you there, Anton. We've had a few people jump in, so I'll just refresh where we're at and what you found here. So, welcome to Building SaaS on AWS. We're talking about shuffle sharding, and we're actually going through some examples with Anton of different models that you can use with multi-tenant applications and how each is impacted by noisy neighbors. So we've done a simple no sharding, and now we're on to a simple sharding model. Thanks,
Awesome.
Anton.
Awesome. Thanks a lot. Right. So let's look what the architecture might look like in this case, right? So the architecture becomes a little bit more sophisticated here, right? So I have a high number of tenants, right? And a number of processors, but it's my core requirement that the number of processors would be significantly lower than number of tenants, right? Otherwise, it's just going to be too expensive, right? The way I've implemented that is I have a dispatcher lambda, right, which has a mapping of tenant ID to processor ID, right, and as those requests are getting into my queue, it just dispatches those requests to a relevant queue, right. So instead of having one processor like in previous example, I got three processors here, right. So the same number of tenants, but more processors. Now, how does that a system behaves, right? That's the $1 million question. So same premise, right? You can take a look at the results here, right? So you can see that the picture, seems to be pretty similar here, right? But if you look closer, you can actually see that not every single tenant is affected, right? You can see that the number of affected tenants is significantly lower. Okay, and if I bring up numbers here, you can see that out of all the tenants, right, only 3 tenants were affected. Out of 20 tenants, only 3 of them were affected. And if you recall me saying in the very beginning, 20 is our noisy neighbor. So
Yep.
noisy neighbor is making it hard on himself, right? But they're also affecting only 2 other tenants. All the other tenants, they're still, alive
Happy.
and kicking. They're still very happy tenants, right? So, with this simple technique, right, we've managed to get our fault tolerance to a much higher level, right? So
Yep.
just to give you some numbers, right, if you have 10 processors, right, 10 of those processors, and only one of them is affected, right, 1 out of 10, right, you're only affecting 10% of your tenant population, right, not 100% like in the previous example, but only 10%, right, which is still, there's place for improvement, right,
Yep.
but this is already significantly better than affecting every other tenant. Okay.
Cool. Very, very cool.
Yep. Yep.
Yep.
Okay. So before I go to the to the awesome shuffle sharding, any questions so far? I don't see chat. Maybe we have some questions in the chat.
No questions on the chat so far, Anton. But please, if you've got a question around shuffle sharding, very cool topic that Anton is describing today, then
Mm-hmm.
please put questions in the chat. In the meantime, I'll ask some questions around each of these models, Anton.
Yeah,
So
absolutely.
you're we're talking about these models before we then lead into shuffle sharding. But what are the pros and cons of each of these, and why? What would you usually see shuffle sharding helping with? So it's really two questions in one there.
That's a good question, right? As with any, architectural models, right? There's obviously, cons and pros for each one of them, right?
Mm.
Well, you know what? Let me start screen sharing for a minute, right? So I can properly answer this question. Okay. Okay. So if you want to stop screen sharing,
Yep.
because
Let me
man,
remove that.
you're stealing my thunder.
Sorry.
I'm
I
kidding.
saw another J meter screen. It's
I'm
like I
kidding.
get
I'm kidding.
mesmerized.
I'm kidding. Right. So one of the well, I'll talk about two major ones, right? That falls in the cons and pros, right? Cost, right?
Yeah.
Obviously, right. If you plan to have multiple shards, right, multiple environments, right, there's a cost, parameter there as well, right? So if you have one queue versus multiple queues, cost, right? So
Yeah.
more sophisticated your environment is, right, more components you put there to make it more resilient, right, you have to consider cost. Okay.
Yep.
Another thing is, besides cost, is complexity, right?
Mm.
Implementing shuffle sharding versus a single lambda function that just pulls from SQS, you can probably you can probably see that the level of complexity is
A little
different.
bit more.
Okay,
Yeah, yeah, a
exactly,
little bit more.
exactly. But right,
Mm.
I wouldn't recommend just go with shuffle sharding from day one, right? And this is absolutely what we need to do. No, shuffle sharding is a pretty advanced technique, right? You can get to super high levels of resiliency, right, of availability, etc., right, without shuffle sharding, right? It's not I would imagine not every single highly available service on this planet uses shuffle sharding. Okay, but shuffle sharding gives you that a little bit extra. Okay, and once you see once I start actually talking about shuffle sharding, it also gives you a component that it's harder to achieve without it. It gives you dynamic recovery. Okay, so
Mhm.
if we talk about fault tolerance, if we talk about resiliency of your system, right, it's not only isolating failure, right, it's
Yeah,
also dynamic recovery, right? So okay, I've isolated those like 3 tenants, right, and now only they are affected, right, and all the other tenants, right, all the other like 10% affected, 90% not affected, right? So this is definitely better than everyone affected. But
yeah,
what can I do to dynamically heal my system, right? So even if I have a noisy neighbor, can I somehow rebalance stuff around, right? Can I do something, right, that will actually affect even smaller number of tenants, right? So how
yeah,
can I make it even better for my tenants, right?
for
So
sure.
that's a different pro of shuffle sharding.
Yeah, nice, nice. And if you mentioned anything else would help with, do you help as well as that, or do you want to jump into the demo and will I
Well,
try to steal your thunder?
let's do the quick demo, right? Because I do
Yep,
also want to do some stuff dynamically, right?
yep.
And then we can we can take it
Okay.
to any discussion you want. Okay.
Well, let's see. Let's just try and quantify some of the improvements of shuffle sharding with the demo.
Mhm. So let me talk a little bit, right? I promise you, I got what I think like 2 slides left, something along these lines, right? Just to show the architecture.
Mhm.
Okay. So what is shuffle sharding? Okay. Now, in previous example, we talked about randomly assigning a tenant to a processor. Okay. But what if instead of assigning a single tenant to a single processor,
Yep.
I assign a single tenant to multiple processors, right? And this is what I'm going to call my shuffle chart. So,
Yep.
this is to explain where the term shuffle coming from, right? So imagine a deck of cards, right? And I'm shuffling that deck of cards, and I'm randomly picking like 4 out of 52 cards or 6 out of 52. So this is exactly what I'm doing here. I have a deck of processors, and I'm randomly and I'm shuffling them, and I'm randomly picking a small number, right, out of that deck of processors. So on this slide specifically, I decided that I'm going to be using 2 processors per tenant. So for example, tenant 1 might be assigned to processor 1 and processor 2, and tenant 4 will be assigned to processor 2 and processor 3. So what it actually means is if my tenant 1 is the noisy neighbor, tenant 4 is going to be affected, but
Mhm.
it will only be affected on one of the processors. So tenant 1 will start sending a lot
Yep.
of
Nice.
traffic, and that
Yep.
traffic will be distributed across multiple processors. So already the load on processor 2 will be lower, right? And tenant 4, right, it will be affected by processor 2 taking more requests from tenant 1. But first of all, we already said that the load on processor 2 will be lower, and tenant 4 also have processor 3, which is not affected, right? So in theory, tenant 4 is a much better state here, right?
Yeah, for sure.
Right.
Yep.
And if we think about this one step further, so as I said, can I actually add a heuristic here of sorts, right,
Yep.
that will allow me to automatically rebalance load? So to show you an example of that, and you're going to see that in like real running environment in about 5 minutes, right? Maybe even less, right? What if I assign like a heuristic like business to each one of my processors, right? So since tenant 1 is a noisy neighbor, right?
Mhm.
Let's say processor 1 is considered as business equals high, processor 2 business equals high, processor 3 business equals low. And that component that dispatches tenant jobs right to those processors, it can be smart enough to decide, okay, so tenant 4, I got one super busy processor and one processor that is barely doing anything. You know
Yep.
what? This is what I can do. I'm temporarily disconnecting tenant 4 from this busy processor because I know it's busy, right? There is no reason to load it even more, right? And
Cool.
I'm going to be channeling 100% of those jobs, right, to processor 3. Yep, it's now busier than it was before, right? But still, tenant 4 is getting much better performance.
There's
So,
one question. One
yep.
question, Anton, what we got from Dean. He's asking, do the processors have to cache data if it has to serve a random tenant every few cycles?
I'm going to show that. I'm actually going to show
Okay.
that on the next slide. I'm going
Cool.
to show that, right? And again, right, there is no like right or wrong answer here, right? It's the way I've implemented it, right? In my prototype, right? But I'll address that in the next slide. That's actually a really good question.
Yeah.
Okay. So, this is what it might look like, right? Each tenant is assigned to multiple processors. It can be 2, 3, 4. We're going to be talking about numbers, in the last slide. So this is the architecture of shuffle sharding, right? I still got multiple shards, right? And I got this component, another lambda, right, which I called refresher. And in my experiment, right, what this lambda is doing, right, it's starting every minute. I trigger it every minute. And every minute, it will get the number of messages in these queues, right? And that's my busyness heuristic, right? I consider my
Oh,
queue.
yeah.
I consider my processor busy if it has, highest number of messages in the queue, right? And then I rate them by the number of messages in the queue. So essentially, if I got a queue with 10 messages and a queue with 1,000 messages, obviously I do not want to send more jobs, to the queue with 1,000 messages,
1,000. It's got enough
right?
to do. Yeah.
Yeah, exactly. And yes, it's updating this processor's database, DynamoDB table, right, which dispatcher grabs, right? Specifically to the question that was asked, yes, I'm caching that information in dispatcher for, if I recall correctly, for something like 30 seconds. Okay, but yeah, because I do not want the dispatcher to go to the database, for every single request, right? That would be heavily overloading the database. And I do know that the refresher gonna do its job every 60 seconds. So I'm refreshing the data. I think either every 30 or 45 seconds. I don't remember the exact number. Okay.
Cool.
I hope this
Cool.
answered
Well,
the question. Now we're gonna
let
see
us
it in
know, Dean,
action.
if that answers the question for you.
Now
Cool.
let's see what's going on, right? So if you recall, right, we have a JMeter running in the background, right? Let me show you the JMeter. Take a look. I hope you can see it. It's still small. I apologize for that. But you can see that the number of samples for tenant 20 is significantly higher than, all the other tenants, right? It's like almost 40K and those are at 2K, right? So you can definitely see noisy neighbor here.
Naughty tenant 20.
Yeah,
Yes.
yeah. But if you look at the, you know what? Let's do the cooldown. I'm going to go to 10 and 20. I'm going to change that to 1 again, right? Because I think we got enough data. So this tenant is no longer noisy. And I'm going to restart my JMeter, right? And we'll see live what's happening. We'll see the cooldown, right? The recovery live. Okay. So, well, you can already see stuff going
Yeah,
on
there
here.
it goes.
But
Yeah.
let's change this to last 30 minutes. Okay, just to show you the whole period. Okay, so this is where we were at the very beginning, right, of the discussion, right? This is the, peace and quiet. This is no noisy neighbors, right? This white space is when demo gods were not favorable with us
we
and
forgot to
JMeter
do
is
our
done.
offering. Yeah,
That's right.
we didn't
That's right.
offer.
Right.
Yeah,
So this
our
is
fault.
the gap, right, where I had to restart JMeter, right? But immediately after that gap, you can see, noisy neighbor kicking in. Now, if you recall previous examples, like previous slides, okay, that I showed, some tenants were spiking, right? Some were down, but some were spiking. Now, if you look here, right, you can see that those charts are going up and down, right? And they are pretty messy, right? But if you look at the top one, it never goes above, a little over 600 millisecond, right? So yes, the response end-to-end execution time, right, was around 400 milliseconds, a little over 400 milliseconds before, right? And for some tenants, it might grow, right? For some tenants, it might go down. But if you look at the numbers here, right, for each one of those data points, it's still around a little bit over 400, right? Those spikes is what's happening when one of the queues is getting full, right? And one of the tenants is essentially, not getting its stuff processed fast enough. But what happens after 60 seconds is rebalancing, right? So essentially, the busiest queue is no longer getting new jobs, right? New requests, right? So the system rebalances itself,
Nice.
right? So, and this is, you can see, right? As you can see, right? It will take few more minutes, right? But you can actually see that this, jumpy charts, right? They're starting to be much more aligned, right? They're starting to be much more similar to what we had in the
Let's
beginning,
start.
right?
Yeah. Yeah.
So I'm going to change back to, let's say, 15 minutes, right? Just to show that it's starting to straighten out, right? And you can see that the execution count for that tenant dropped,
Let's drop.
right?
Yeah.
And you can see that the number, right, is getting back on track, right?
Cool.
So essentially, yes, we had some noisy neighbor problems in our environment, right?
Hmm.
But by tweaking, right, capacity, by tweaking that refresh, right, I got to a point where, okay, I got a noisy neighbor, right? I can probably get alert for that noisy neighbor, but that noisy neighbor, it's not really bothering anyone else besides me, because I do know that I have a noisy neighbor. Okay.
Yep.
Now
Yep.
we're talking about noisy neighbor here, right? But this can be any other issue, right, in my system. Okay.
Yep. Like what sort of issues? So what is it's all around. It seems to be around stuff like noisy neighbor, around fault tolerance. But what else would it solve potentially?
Well, that's an interesting topic, right? We can open a whole discussion around that,
We
right?
have about 15 minutes left. Yeah.
So I would say it can solve many problems, right? Noisy
Mm,
neighbor is obviously one of them, right? But imagine poison pill, right? Where one of your processors, right, is stuck, right, or completely down, right?
mm,
Imagine some problems, not necessarily with the whole processor, right, but maybe something more fine granular, right? Because we're talking in a serverless context here, right?
yep.
But at least from my experience, right, not every single serverless application is 100% serverless, right? So you might have some non-serverless components there as well, right, which are up to capacity. Okay,
Yep.
so the idea here, and yes, I've built it around a noisy neighbor, right, because that's the major use case that I have: noisy neighbor and poison pill. But
Hmm.
the idea is, it helps you to isolate failure, right? It helps you to improve fault tolerance, right?
Yep.
So I definitely see this approach addressing other concerns as well.
What about things like backups? Would you need something like backups in this solution?
Backups for what?
Any of
Uh,
the data that's in say in the queue or in as part of the flow, would you need to
mhm.
back it up at all, or is there a strategy to avoid that?
uh, Well, I did not consider backup specifically, right, when I was building this, right? I'll admit
Hmm.
that, right? Now, if you do have some databases somewhere here in the model, yes, obviously, right? Databases require backups, right? It depends how, the tenancy that you require, right? Whether you're going to be using, one instance of database for all tenants and you're just
Yep.
doing shuffle sharding for your compute or processing piece, right? Or you're going to be using database per tenant. So I think factors important for backup decisions here is how stateful your solution is, right? So if your solution is stateful, right, yes, you would most probably need some backups in place, right?
Yep.
I'm always aiming to create my compute layer, right? The place where magic happens, right? Not the persistence, but the compute layer. And
Yeah, magic.
I'm saying compute, but I don't necessarily mean just Lambda, right? It can be queues, it can be it can be anything, right? That deals with processing data. I usually tend to recommend to make it as stateless as possible, right?
Yep.
Because if it's stateless, it's easy to destroy old ones, create new ones. And with shuffle sharding, right, maybe you started with 50 shards, right? But as your number of tenants grow, you want to go into 100, right? Or maybe,
Yep.
you figured out that it's too expensive and you want to scale down, right? So having that set up as stateless is going to help you, right? You don't need to back up stateless stuff. You do need to back up, your cloud formation template that will create
Mm.
it, right? But as for data, data is more relevant to the persistence layer, right? I
Yep.
hope this
Okay.
answered the question.
Yeah. Yep. For sure. What about say for example one of the queues fail? What if you what would happen in that
Oh
scenario?
man. So one of the queues or one of the functions? Well, I mean, is the queue specific or anything?
So it just say if somebody shut down one of the queues, what would happen
Hmm. Okay.
in your scenarios?
I haven't tried that, but let's see what we can do here, right? So let's see, how do I disable the queue, right? Well, let's make it simple, right?
Do you want to
Let's,
share screen or
well,
anything?
yeah, I'm sharing my screen. I'm sure. Can you enable it? Okay.
Yep.
So let's say I got my functions here, right? Those are my processors, right? Well, let's say I'm unable to pull from one of the queues, right?
Hmm.
Let's say, right? I haven't tried that before, so if things going to explode, right? So what I'm gonna do, right, from the top of my head, let's go to the concurrency settings of that processor and let's change that to 0, right?
Yep.
So 0, right? So basically, this function is always gonna be throttled, right? So nothing will be pulled from the queue, right? Let's save that and let's see what happens, right? You actually got me curious, right? It will take a couple of minutes, right,
Hmm.
for things to kind of start showing up here.
Yep.
Thinking
Yep.
about it, right, I think I do have enough capacity here for the system to continue to work as is. Okay, so since there were messages continuously in the queue, right, and being processed, at the moment, tenants that are using the processor number 1, right, some of their messages, some of their requests are stuck in that queue, right, and there
Yep.
is no one who can process them, right? So the data is not lost, right,
Hmm.
but it's halted, right? So I can imagine, right, let's give it like a minute or two. I can imagine the moment I re-enable that function, we're going to see a big spike in the
Big spike.
execution
Yeah.
duration
Yep.
because those jobs were stuck in the queue. But as of now, right, let's see what happens, right? So
Mm.
I usually ignore the rightmost column here because that data updates, right? But from what I see here, right, yep, we got a small spike here for one of the tenants, right? But from what I see here, the system is still
It
up and
just
running.
kept going.
It's
Yeah.
still
Nice.
up and running, keeps going. You can
Yep.
actually see some interesting data, right? I got here for P1Q and P1 function, right? I got a lot of metrics here. So you
Yep.
can see, for example, that the number of messages not visible here, well, the number of messages not visible is growing, right? So and imagine the blue line, the visible messages will start growing as well soon, right? Because you got messages in the queue that no one is processing. Okay, so you
Yep.
will see the reflection here. And the orange line here that represents the P1 functions, that throttles. Okay, so essentially my function is being continuously throttled, right? It doesn't run, right? So I can immediately see that reflected here.
Yep.
Okay, so
Yep.
yeah. I
That's
mean, thanks for testing the system. I think it's still up
That's
and running.
fantastic. Well, this is what the show's all about, how we can improve our resiliency with our SaaS application. So
Hmm.
that works really well. That's
Hmm.
very cool.
Let me
Very cool.
re-enable that, right? Let me
Yeah,
just
yeah. Let's see what
quickly
happens when you turn it
re-enable
back
that because
on.
you got me curious, man. It's 11. Good enough, right? It's past 9 p.m. here in Austin, right? And you got me super curious about what's going to happen. So I'm expecting a spike here for about what we talked about 2 minutes, right? A
Mm,
spike here for few invocations, right? That were stuck in that queue, and after that things will get to normal, right? And that's
yep.
because if you remember, I'm measuring end-to-end execution duration. Oh yeah, there it is. There
There
it
it
is.
is. Yep.
Okay, there it is, right? So yes, right. The the numbers here are so low you cannot see them, right?
And then boom.
But you can actually see the tenants that were affected, right? If you look
Uh,
here, oops, if you look here at the bottom, you can see 1, 2, 3, 4, 5, 6 tenants that were affected by the outage of processor
the
one,
queue. Yeah.
right?
Yeah.
Okay, and the things will get back to normal in a minute or so, right?
Yep.
Okay.
Recovering. It should recover nicely.
Yep,
There you go.
yeah. It's
Nice.
getting lower.
Yeah.
Okay.
Yep.
If I do disable enough, capacity, right? Like if I shut down half of my system, the picture
Mm,
will probably be different, right? So,
mm,
it
yeah.
depends how much spare capacity you have. Okay.
Cool. Well, that was my resiliency question. That was cool. No, the demo gods, very good. Thank you. See, sacrifices work, Anton. Sacrifices work. The other question I had was, yeah, exactly, Bill. The demo gods are pleased. So the other question I have, Anton, for you is all around security. What sort of security considerations or guardrails would we have to think about if we want to implement something like shuffle sharding?
That's a good question, right? Let me think about that. Because I mean, security, this is a topic for another 4-hour session. So
You
I
can
would
always
say,
come back.
yeah, I don't mind. I don't mind. Right. So as I said, right, in the beginning, right, you usually shuffle sharding, at least from what I see, right, that's not your first architecture. Usually we starting with something simpler and you evolve into shuffle sharding when you think you need it, right, when you think there is a merit to that architecture. So the security approach, right, I would say it depends where you're originating from, right? So if you're moving from that architecture of everything is super multi-tenant, right? Everything is managed, by a single processor, right? Everything is shared, and you're moving to multiple processors, that's one thing, right? So you're probably, you know, you're, improving your security posture a little bit here, okay? Now, if you're moving the other direction, where every single tenant got their own isolated environment, and you're moving into that, sharded but still multi-tenant architecture, right? You do need to understand, the consequences of that, right? So, for example, how you treat data isolation, right? Is it okay, right? For, let's say, that dispatcher function, right? If you recall, right, in the way I've built it, it will have access to jobs and requests of every single tenant, right? Essentially,
Yep.
that's your one piece, right, that
Yep.
processes data for every single tenant, right? So, for example, one of the things you might do here, right, and from the top of my head, right, is you might want to have some tenant-specific encryption, right, of your jobs, right, and the decryption keys will only be available to relevant processors, right? So that dispatcher that has access to all the tenants, right, it cannot really do anything with that data since it's encrypted, right? You can
Yep.
also think about like dynamic IAM permissions based on that, right? So whenever dispatcher is getting a job, right, it can only send it to a particular processor. So
Cool.
security is important, right?
Yep.
Shared resources, right? If you're moving from a single tenant approach to multi-tenant approach, you always have some security considerations, thoughts, and planning, right? I would say it depends what exactly you're doing there, right? And
Okay.
the key thing here is to understand what you're doing, right?
Yep.
Understand what's coming with multi-tenancy, right?
Yep. Yeah, for
Yeah.
sure, for sure. Yeah, great answer there, Anton. Sorry for springing all these questions on you.
No, that's awesome. That's all. Keep them coming. Keep them
Game
coming.
Comics. I probably got one more. So, what if you wanted to deploy this model multi-region? Well, you know, just say you wanted to,
No,
because
no, that's a
just
good
say you
one.
wanted to. Yep.
Uh, I haven't tried that, right? I don't see any reason, right? It shouldn't work, right? Because that was the idea, right? It's not just deploy all those shards in a single account and single region, right? We're talking serverless, right? So, Lambda, right?
Yeah.
SQS. If you
Yeah.
deploy
Yeah.
everything in a single account and single region, right? All of them will have the same quotas, right? The same concurrency quotas and other, API request quotas, right? So you can definitely make your environment better by spreading it across accounts and regions, right?
Yeah.
I haven't tried that, and unfortunately, I don't think we have time to actually try it like we did like that, experiment
No,
before.
we are running out of
Yeah,
time, but if
I don't
someone,
see a reason why it shouldn't work, to be honest. Right, I
yeah,
definitely don't see a reason why it shouldn't work. So yeah, spreading the processors across multiple regions for added resiliency, sure, why
yeah,
not? Right, that's the whole
yeah.
reason we're doing that.
Yeah, but as pointed out, it's quite complex as well to do that. But
Hmm.
hey, it may be a use case. The business may require multi-region tenancy, so that's very very valid, and we see customers doing that. So I thought we are just coming to the end. Have you any final thoughts you'd like to share, or shall we let our viewers go. If you just joined us, by the way, this is Building SaaS on AWS, and you've just missed an excellent talk with Anton all around shuffle sharding, how you can add resiliency to your application, and how to actually implement it using serverless applications. And you missed it. So if you can grab it on the video on demand of the previous shows, and it's all good. Is there anything else you want to end with, Anton? Any
Well,
slides or anything you want to end on?
well, I do have one more slide that I want to show very quickly. We got 5 minutes, so I'll try to
Yep.
take no more than 1 minute, right? Can you please help me to share my screen and tell me
I
once
sure
you see
can.
it?
I have the power.
Once you see it, right? And it's going to be a very boring slide with a lot of numbers, right? It's going to be super exciting for math flowers like myself, right? But the idea is, right, this shuffle sharding, it sounds awesome, right?
Mm-hmm.
But what happens if, by the magic of combinatorics and random number generators, you have multiple tenants somehow assigned to the same processors? Well, you know what? Random, right? It can happen, right? So it would be great to see what's the probability of that. And this is exactly where you understand the benefit of shuffle sharding, right? So I got a few use cases, a few calculations here, right? And feel free to screenshot that, right? You have a very similar table if you Google shuffle sharding, right? So this is not just me doing math. And the idea here, right? I hope you can see my mouse pointer, right? Is different
Yep.
numbers of processors, right? So the demo I showed you, right? The slides that I showed you, right, were 8 processors and 3 tenants, right? So with 8 processors and right, 8 processors and 3 processors per tenant, right? With that number, right, you're getting 56 combinations. So you have 56 distinct combinations. So the probability of 2 different tenants using exactly the same combination is roughly 2%, right?
Yep.
Pretty low, but you know what? Not as low as I would like it to be, right? As
Mm-hmm.
you start to have more processors and bigger shards, right? Even with the same number of processors per shard, right? You can see how those numbers exponentially become lower, right? So, with 50 processors and still 3 processors per tenant, right? The shard size is 3 processors. Your number of combinations is almost 20K, right? So the probability, right, of 2 tenants using exactly the same shard is 0.005%, right? And if you look at 3 tenants and 4 tenants using exactly the same shard, it's even lower. So what it actually means, right, statistically, right, this scenario, if you have 20,000 tenants, approximately 20,000 tenants, because it's a little bit higher than 5 here, a noisy neighbor will not affect any other tenants, right? For 100,000 tenants, a noisy neighbor will only affect 4 other tenants, right? Affect, I mean, have an impact, because noisy neighbor and those other tenants are reusing exactly the same set of processors, right? Their shuffle shard is exactly the same, right? So those numbers, right? I love to wrap up with these numbers, right? And I think
Yep.
we can stop sharing right now, right? Because
Okay.
they do illustrate how awesome this technique is, right? Once you get it at a scale, right? So yeah,
Uh,
that's something I do want to wrap up with. We've shared a few links, right, that talk about shuffle sharding. It's
yep.
an awesome technique, right? It's not, I wouldn't call it like a reference architecture or anything. It's a technique, it's a methodology. It can be applied in a non-serverless world, serverless world, right? And you've just seen live how applying shuffle sharding, right, even for small number like 20 tenants, right, immediately improves the noisy neighbor problem and adds resiliency to your system. So yeah, I'll stop with that. I think we're up at a time.
Cool, Anton. Thanks so much. I've pushed all those links on the feed, so if you have just joined us, you've missed the show, but you can catch us on video on demand, either on Twitch on this channel or our YouTube channel. So yeah, if thanks. I'd just like to thank Anton for joining us and providing such great level of detail and content. Thanks very much, Anton.
Absolutely, my
Did
pleasure.
you did you have fun?
Oh, absolutely, definitely, definitely.
Awesome.
You can probably see I'm excited. I'm enjoying talking about this stuff.
Yeah,
I'm a techie.
yeah. Even if it's 9:30 at night for you, you brought the energy. It was fantastic.
Not a
Thank you very
problem.
much. I hope everybody enjoyed it. Enjoyed listening to this talk today. We will be back in another 2 weeks, same time, same place, to talk more about building SaaS on AWS. But until then, we'll see you next time. Bye.